Hello everyone, I'm Professor Chia-Po Wei. If you want to contact me, you can write emails. I will post the course information both on the announcement board of the Cyber University and on our course website. In each week, I will provide a pre-recorded lecture video in English. In each week, there will be a quiz which starts from Monday 8:30 a.m. to 8:45 a.m. via the Cyber University. If you have questions after watching the video, you can use the TA hours, which is on Tuesday from 16 o'clock to 18 o'clock, and on Thursday from 10 a.m. to 12 a.m. at the EC building of A011-2. There will be an examination on May 26th. The time is from 18 o'clock to 20 o'clock. The scope will cover sections 3.5, 3.6, and the whole chapter 4. If you have any questions or problems about the examination, you can contact me. In this week, we will go through section 4.1, linear transformations. I will introduce the definition of a linear transformation, which plays an important role in mathematics. I will also give a number of examples about linear transformations. In section 4.2, we will show that every linear transformation can be represented as a matrix. In section 4.3, we will consider the relationship between different matrices that represent the same linear transformation. A transformation is actually a function or a mapping. In this slide, we will revisit the definition of a function. There are 4 figures, A, B, C, D, in this slide, and each figure represents a relation between 2 sets. Which relation is a function? The correct answer is figure A and figure D are a function, while figure B and figure C are not a function. Because for a function, every element in the input space must have a mapping, but there is one element in the input space of B that does not have a mapping, so figure B is not a function. Figure C is also not a function, because for a function, every element in the input space can have only one mapping, but there is one element in the input space that has 2 mappings. Thus, figure C is also not a function. For a function, the input space is called the domain, while the output space is called the codomain. Every element in the domain must have one mapping to some element in the codomain, and every element in the domain can have only one mapping. If it has 2 mappings, then it is not a function. A transformation is also called a function or a mapping. A linear transformation is a special type of function that need to satisfy 2 properties, the additivity property and the homogeneity property. Next, we give a formal definition of the linear transformation. A mapping L from a vector space V into a vector space W is said to be a linear transformation if the following 2 properties are satisfied. The first property is the additivity property, which requires L to satisfy L of V1 plus V2 equals L of V1 plus L of V2. The second property is the homogeneity property, which requires L to satisfy L of alpha times V equals alpha times L of V. The two properties need to be held for all V1 and V2 in the vector space and for all scalars alpha. We know that for the additivity property, on the left-hand side, the linear transformation is applied after the vector addition, while on the right-hand side, the linear transformation is applied before the vector addition. The equality means that the linear transformation preserves vector addition, since it does not matter whether the linear transformation is applied before or after the vector addition. Similarly, for the homogeneity property, on the left-hand side we see that the linear transformation is applied after the scalar multiplication, while on the right-hand side, the linear transformation is applied before the scalar multiplication. And the equality means that the linear transformation preserves the scalar multiplication, since it does not matter whether the linear transformation is applied before or after the scalar multiplication. An equivalent definition of a linear transformation L is that it satisfies L of alpha times V1 plus beta times V2 equals alpha times L of V1 plus beta times L of V2 for all V1 and V2 in the vector space and for all scalars alpha and beta. This definition is a combination of both the additivity and the homogeneity property. When proving a mapping is a linear transformation, you can either use the first definition or the second definition. We use the notation L column V arrow W to denote a mapping L from a vector space V into a vector space W. In the case that vector spaces V and W are the same, we refer to a linear transformation L column V arrow V as a linear operator on V. That is to say, a linear operator is a transformation that maps a vector space V into itself. We use example 1 to illustrate the linear transformation. Define a mapping L as L of x equals 3 times x for each x in Rn. We will show L satisfies both the homogeneity property and the additivity property. To prove L satisfies the homogeneity property, we consider L of alpha times x. By definition of L, this equals 3 times alpha x. Since 3 and alpha are scalars, we can exchange their order and have alpha times 3x, which again, by definition of L, this is equal to alpha times L of x. Since L of alpha x equals alpha times L of x for all x in Rn and all scalars alpha. Therefore, L satisfies the homogeneity property. To prove L satisfies the additivity property, we consider L of x plus y. By definition of L, this can be written as 3 times parentheses x plus y, and this is equal to 3x times 3y. Then by definition of L, we know 3x is L of x, while 3y is L of y. Since L of x plus y equals L of x plus L of y for all xy in Rn, and therefore L satisfies the additivity property. Since L both satisfy the homogeneity and the additivity property, it follows that L is a linear transformation. Note that L is also a linear operator since it maps Rn into Rn. Next, we visualize the linear transformation in R2. Let x be a given vector in R2. Then L of x is 3 times x. That is, the linear transformation L enlarges the vector x by a scale factor 3. And this operation is known as scaling. We have shown that scaling is a linear transformation. Next, we consider another example of a mapping on R2. Consider a vector in R2 where the first entry is denoted as x1 and the second entry denoted by x2. We define a mapping L as L of x equals a vector in R2 where the first entry is minus x2 and the second entry is x1. We also define another vector y in R2 as y1, y2. We want to prove that L is a linear transformation, so we have to show L satisfies both the homogeneity and the additivity properties. To this end, we consider L of alpha x plus beta y. By the definition of L, and this can be written as a vector in R2 where the first entry is minus times parentheses alpha x2 plus beta y2. The second entry is alpha x1 plus beta y1. Then this expression can be written as alpha times a vector minus x2 x1 plus beta times a vector minus y2 y1. And note that by definition of L, the vector minus x2 x1 is L of x, and the vector L and the vector minus y2 y1 equals L of y. Therefore, we have shown L of alpha x plus beta y equals alpha L of x plus beta L of y. And this equality holds for all xy in R2 and all scalars alpha and beta. And therefore, L satisfies both the homogeneity and the additivity properties. And we have proved L is a linear transformation. Moreover, L is a linear operator since it maps R2 into R2. Next, we visualize the linear transformation L in the R2 plane. Let x be a vector in the R2 plane. Then L of x equals minus x2 x1 Actually, L rotates the vector x 90 degrees counterclockwise about the origin. Hence, L is a rotation operation in the R2 plane. We know that the rotation operation only change the direction of x, but the length of x does not change. In fact, it can be shown that any rotation operation in Rn is also a linear transformation. Next, we consider the mapping M from R2 to R. That is, the input is a vector in R2, while the output is a scalar. The definition of M of x is actually the length of its input vector. And the definition of M of x is the square root of the sum of x1 square and the x2 square. So M of x is the length of the input vector x. We want to show M is not a linear transformation. To do this, we will find an example of alpha and x such that the homogeneity property is not satisfied. To this end, we consider M of alpha x, which is the square root of the sum of alpha square x1 square and alpha square x2 square. If we take alpha outside the square root, then M of alpha x can be written as the absolute value of alpha times n of x. Now we are ready to show that the homogeneity property is not satisfied for some alpha and some x. It is straightforward to see that if alpha is negative, then n of alpha x becomes minus alpha times m of x, and therefore m of alpha x is not equal to alpha times m of x whenever alpha is negative and the x is not the zero vector. We have found examples of alpha and x such that the homogeneity property is not satisfied, and therefore M is not a linear transformation. In this slide, I will present some important consequences for linear transformation. Let L be a linear transformation from a vector space V into a vector space W. Then the following three statements hold. The first statement states that L mapped the zero vector in V to the zero vector in W. Here, 0v and 0w are the zero vectors in V and W respectively. To prove the first statement, we will use the homogeneity property, which states that L of alpha V equals alpha times L of V for all scalars alpha and all vectors V. If we select alpha as 0, then L of alpha V becomes L of 0 times V. And if we select alpha as 0, then alpha of L of V, then alpha times L of V becomes 0 times L of V. We know that due to the vector space axiom, 0 times v equals the 0 vector in v, while 0 times any vector in w equals the 0 vector in w. Hence, we have proved L of 0v equals 0w, and statement 1 is proved. The second statement states that if v1, v2 up to vn are elements of v, and alpha1, alpha2 up to alpha n are scalars, then the following equality holds. This equality means that L maps the linear combination of v1, v2 up to vn to the linear combination of L of v1, L of v2 up to L of vn. That is, the linear combination is preserved under a linear transformation. Statement 2 can be proved by mathematical induction and is left as an exercise to you. Statement 3 states that L of minus v equals minus L of v for all vector v in the vector space. To prove statement 3, we will use the result of statement 1. And from statement 1, we have 0w equals L of 0v. Due to the vector space axiom, 0v can be 0v is the sum of v plus minus v for any vector v in the vector space. And due to the additivity property of a linear transformation, we know L of v plus minus v equals L of v plus L of minus v. And from the last equality, we know that L of minus v is the additive inverse of Lv. That is, L of minus v equals minus L of v, and the proof of statement 3 is finished. Next, we consider another mapping on R2. Let A be a fixed non-zero vector in R2. We define the mapping L of x as x plus A. This operation is known as a translation. A translation is the addition of a constant vector A to x. We will show that a translation is not a linear operator. We know that L is a mapping from R2 to R2. To show that L is not a linear operator, we will use the first statement in the previous slide. If L is a linear transformation, then we must have L of 0v equals 0w. In our example, v and w are both R2, and therefore, if L is a linear transformation, then L of the 0 vector in R2 must equal the 0 vector in R2. But for this example, we have L of 0 equals 0 plus A, and since A is a non-zero vector, therefore L of 0 is not equal to the 0 vector in R2. So L is not a linear transformation. We can visualize the translation operation in the R2 plane. Let x be a given vector in R2. X plus A is the translation of the vector x by a non-zero vector A. We know that L of x does not pass through the origin,
because L of 0 does not equal the 0 vector, and therefore L is not a linear transformation. If we go back to example 4, recall that the rotation operation is a linear transformation. Therefore, it satisfies L of 0 equals the 0 vector. We can see from the figure that L of x indeed passes through the origin. We can also go back to example 1, the scaling operation. Recall that the scaling operation is also a linear transformation. Therefore, it satisfies L of 0 equals the 0 vector. And we can see from the figure that L of x indeed passes through the origin. Example 9 considers integration as a mapping. Let L be the mapping from CAB to R. Here, CAB is the vector space of continuous functions over the interval AB, and we define L of f as the definite integral of function fx over the interval AB, and the input of L is a continuous function, while the output of L is a scalar. Next, we prove L is a linear transformation. To this end, consider L of alpha f plus beta g. Here, f, alpha, and beta are scalars, and f, g are any vectors in CAB. By definition of L, we have L of alpha f plus beta g equals the definite integral of alpha f plus beta g over the AB interval. Then, by properties of definite integrals, we have this term equals alpha times the definite integral of f plus beta times the definite integral of g. Again, by definition of L, the definite integral of f is L of f, while the definite integral of g is L of g. So far, we have shown that L of alpha f plus beta g equals alpha L of f plus beta Lg, and this equality holds for all scalars and holds for all f and g in uh, the vector space CAB, and therefore L is a linear transformation. Example 10 considers the differentiation operation as a mapping. Let D be the mapping from C1AB to CAB. Here, C1AB is the vector space of differentiable functions, and the CAB is the vector space of continuous functions. We define D of f as f prime, and f prime denotes the derivative of f. The input of D is a differentiable function, while the output of D is a continuous function. The continuous function may or may not be differentiable. Next, we prove D is a linear transformation. To this end, consider D of alpha f plus beta g, where alpha beta are scalars and fg are any vectors in C1AB. Then, by definition of D, we have d of alpha f plus beta g equals the derivative of alpha f plus beta g. Then by properties of differentiation, we have alpha f prime plus beta g prime. And again, by definition of d, we know f prime is d of f, and g prime is d of g. And we have shown d of alpha f plus beta g equals alpha d of f plus beta d of g. And this equality holds for all scalars alpha beta and all fg in the vector space C1AB. And therefore D satisfies the homogeneity and additivity properties, and therefore D is a linear transformation. Let's see exercise 5, which is in page 193 of the textbook. Determine whether the following are linear transformations from R3 into R2. The input is a vector in R3, while the output is a vector in R2. In fact, there is a simple method to determine whether a mapping is a linear transformation. That is, if the output of a mapping L only involves 0, or only involves terms from input X of first order only, then the mapping is a linear transformation. Consider case A. L of X is defined as X2, X3 transpose. Since the output only involves terms from X of first order only, then L of X is a linear transformation. Next, consider case B. L of X equals the 0 vector in R2. Since the output only involves 0, and therefore L is a linear transformation. Next, consider case C. L of X is defined as 1 plus x1 and x2 transpose. For this case, we know that L of 0 equals 1 plus 0 and 0. So the output is 1, 0 transpose. And since L of 0 is not equal to 0, therefore in case C, L is not a linear transformation. And for this case, the constant term is not 0, although the other terms from X are of first order only. For case D, L of X is defined as x3 and x1 plus x2 transpose. Since the output of L only involves terms from X of first order only, and therefore case D is a linear transformation. So in example 5, case A, case B, and case D are linear transformations, while C is not a linear transformation. Let's see exercise 6. Determine whether the following are linear transformations from R2 into R3. The input is a vector in R2, while the output is a vector in R3. In case A, L of X is defined as x1, x2, 1. Note that the third entry is a non-zero constant, and therefore L of 0 equals 0, 0, 1. which is not the zero vector in R3. So L is not a linear transformation. In case B, L of x is defined as x1, x2, x1 plus 2x2. Since the output of L only involves terms from input x of first order only, therefore L is a linear transformation. In case C, L of x is defined as x1, 0, 0. Since the output of L only involves 0 or only involves terms from input x of first order only, L is a linear transformation. In case D, L of x is defined as x1, x2, x1 squared plus x2 squared. Note that the third entry is x1 squared plus x2 squared, which is not of first order. And for this mapping, we can always find examples of alpha and x such that the homogeneity or the additivity property is not satisfied, and therefore L of x is not a linear transformation. In exercise 6, only case B and case C are linear transformations, while case A and case D are not a linear transformation. If the exercise wants you to give a formal proof for a linear transformation, then you should prove that the mapping indeed satisfies both the homogeneity and the additivity properties, as been done in example 9 or example 10. If the exercise wants you to prove that a mapping is not a linear transformation, then you should find some scalar alpha and some vector x such that the homogeneity property or the additivity property is not satisfied. If the exercise only wants you to answer true or false, then you can use the simple method discussed in this slide. Exercise 8 considers mappings defined on Rn times n, that is, matrices of dimension n times n. The input of the mapping is a matrix of dimension n times n, while the output of the mapping is also a matrix of dimension n times n. In case B, L of A is defined as A transpose. We will show L is a linear transformation. To this end, we consider L of alpha A plus beta B. By definition of L of alpha A plus beta B equals the transpose of alpha A plus beta B, which can be written as alpha A transpose plus beta B transpose. Since A transpose is L of A and the beta transpose is L of B, therefore we have proved the equality L of alpha A plus beta B equals alpha LA plus beta LB holds for all scalars alpha beta and all matrices AB in R n times n. Therefore, L satisfies both the homogeneity and the additivity properties, and thus L is a linear transformation. In case C, L is defined as A plus the identity matrix. Note that there is a non-zero constant term in the definition of L, and L is not a linear transformation because L of the zero matrix equals the zero matrix plus the identity matrix, which is the identity matrix and is not equal to the zero vector in Rn times n. Therefore, L is not a linear transformation. In case D, L of A is defined as A minus A transpose, and you can follow similar steps as in case B to show that L is a linear transformation. Exercise 9 considers mappings from P2 to P3. That is, the input of the mapping is a polynomial in P2, while the output of the mapping is a polynomial in P3. In case A, L of Px is defined as x times P of x. Here, x is a constant polynomial. X is not a variable. And the L of P of x is defined as a constant polynomial times the input polynomial P of x. And L is a linear transformation. To show this, we consider L of alpha P of x plus beta Q of x. By definition of L, we have L of alpha P of x plus beta Q of x equals x times parentheses alpha P of x plus beta Q of x, which can be written as alpha times x times P of x plus beta times x times Q of x. Since x P of x is L of P of x and x Q of x equals L of Q of x, and therefore we have shown L of alpha P plus beta Q equals alpha L of P plus beta L of Q. And this equality holds for all scalars alpha beta and all P of x and Q of x in P2. Therefore, L is a linear transformation. In case B, L of P of x is defined as x squared plus P of x. Note that x squared is a constant polynomial in P3, and L of P of x is defined as a constant polynomial plus the input polynomial. Such mapping is not a linear transformation because L of the zero vector in P2 equals x squared. X squared is a non-zero constant polynomial in P3, which is not the zero vector in P3, and therefore L is not a linear transformation. In case C, L of P of x is defined as P of x plus x times P of x plus x squared times the derivative of P of x. The first term P of x is the input polynomial. The second term is the constant polynomial x times the input polynomial P of x. The third term is a constant polynomial x squared times the derivative of the input polynomial. Such mapping L is a linear transformation. You can follow similar steps as in case A to show that L satisfies both the homogeneity and the additivity properties, and therefore L is a linear transformation. In this slide, we will show a matrix can be viewed as a linear transformation. Let A be a given matrix in Rm times n. Then we can define a linear transformation L from Rn to Rm as L of x equals Ax for each x in Rn. The input of L is a vector x in Rn, while the output of L is Ax, which is a vector in Rm. Therefore, L is a mapping from Rn to Rm. We know that L is a linear transformation because L of alpha x plus beta y equals A times parentheses alpha x plus beta y. This equality is due to the definition of L. Then we know A times parentheses alpha x plus beta y equals alpha times Ax plus beta times Ay. Since Ax is L of x and Ay is L of y, therefore we have shown that L satisfies both the additivity and the homogeneity properties for all scalars alpha beta and all vectors xy in Rn. Therefore, L is a linear transformation. In view of the above, we know a matrix A of dimension m times n can be viewed as a linear transformation L, and the L is a mapping from Rn to Rm. Next, we introduce the kernel of a linear transformation L. Let L be a linear transformation from V to W. The kernel of L is defined as the set of all vector V in the vector space V such that L of V equals 0W. 0W is the zero vector in the vector space W. Next, we use the figure in page 18 to visualize the definition of kernel L. Our textbook does not have this figure. The kernel of L corresponds to the blue region in the vector space V, and every element in the blue region will be mapped to the zero vector in vector space W. This is exactly the definition of kernel L, which is the collection of all vectors in V such that L of V equals the zero vector in W. Because of the definition, kernel of L is a subset in the vector space V. We also know that 0V is always in the kernel of L because L is a linear transformation. Therefore, L must satisfy L of 0V equals 0W. And this equality means that 0V satisfies the requirement in the definition of kernel of L. Therefore, 0V is always in the kernel space of L. The null space of a matrix is closely related to the kernel of L. Let A be a matrix in Rm times n. Then recall that the null space of A is the set of all vector x in Rn such that Ax equals the zero vector. Or we can say the null space of A is the set of all solutions of the homogeneous system Ax equals 0. If we define a mapping L of x, if we define a mapping L where L of x equals Ax, then L is a mapping from Rn to Rm. In this case, the null space of matrix A is exactly the same as the kernel of L. To see this, know that V corresponds to Rn, while W corresponds to Rm, and L of V equals the zero vector can be written as Ax equals 0. Therefore, the null space of A is exactly the same as the kernel of L. We introduce the image of a linear transformation L. Let L be a linear transformation from V to W, and let S be a subspace in V. The image of S, denoted by L of S, is the set of all vectors in W, such that W equals L of V for some V in the subspace S. Note that L is a mapping, and S is a subspace in V, and L of S is a subspace in W, which will be proved later. You only need to remember that L of S is also a subspace which is in W, and every element in L of S must satisfy the requirement W equals L of V for some V in the subspace S. If we choose the subspace S as the entire vector space V, then L of V is called the range of L. We use the figure in page 18 of the slides to visualize the image of S under L. Let S be a subspace in the vector space V, and L is a linear transformation from V to W. Then L of S is the gray region in vector space W, and L of S is the mapping of the subspace under the linear transformation L. Every element in L of S, every element in L of S, which is denoted by W, must satisfy the requirement W equals L of V for some V in S, which means for every W in L of S, we can always find some V in S such that L of V equals W. Next, we show that 0W is always in the image of S. To prove this fact, we need to show 0W satisfy the requirement in the definition of image of S. That is, we need to show 0W equals L of V for some V in the subspace S. How to find such vector V in S? And we can use the following observations. The first observation is that 0v must be in the subspace S. This is one property of the subspace. It must contain the zero vector. So we have 0v is in S. The second observation is that L of 0v equals 0w because L is a linear transformation. By the two observations, we know 0w equals L of 0v, where 0v is in the subspace S. Therefore, 0w satisfies the requirement in the definition of image of S. So 0w is always in the image of S. We show the relationship between the range of L and the range space of a matrix. Let A be a matrix in Rm times n. Recall that the range space, or the column space of A is the collection of all linear combinations of column vectors of A, which can also be expressed as the collection of vector B in Rm, such that B equals Ax for some x in Rn. If we define the mapping L as L of x equals Ax, then the range space of A is exactly the range of L. To prove this, note that L is a mapping from Rn to Rm. Therefore, V corresponds to Rn and W corresponds to Rm. The range of L is the image of the entire vector space. That is the image of V, or the image of Rn. So the range of L is L of Rn, which is the set of all vector B in Rm such that B equals Ax for some x in Rn. If we compare the definition of Ls and the definition of L of Rn, we know that W corresponds to Rm and L of V corresponds to Ax, and the subspace S corresponds to V, which is Rn. Therefore, the range of L is exactly the same as the range space of A. In this slide, we will prove theorem 4.1.1. If L is a linear transformation from V to W, and S is a subspace of V, then the following two statements hold. Statement 1 states that kernel of L is a subspace of V. Statement 2 says that L of S, which is the image of S under L, is a subspace of W. Next, we will revisit the definition of a subspace. If S is a non-empty subset of a vector space V, if S satisfies the following two properties, then S is said to be a subspace of V. The first property means that S is closed under scalar multiplication, because every because every vector x in S, the result of scalar multiplication alpha x is still in S. The second property means that S is closed under vector addition. If x and y are vectors in S, then the result of vector addition x plus y is still in S. So if S is both closed under the scalar multiplication and the vector addition, then S is a subspace of V. In the next slide, we will prove statement 2. And statement 1 can be proved in a similar way, and is left to you as an exercise. If L is a linear transformation and S a subspace of V, then L of S is a subspace of W. To prove this, we need to show three things. First, we need to show L of S is non-empty. Second, we need to show L of S is closed under scalar multiplication. Third, we need to show L of S is closed under vector addition. First, we prove that L of S is non-empty. Because 0W is always in L of S. Therefore, L of S has at least one element. We have shown this fact in the previous slides. Next, we show L of S is closed under scalar multiplication. The idea is that if W is in L of S, we want to show alpha W is also in L of S for any scalar alpha. If W is in L of S, then by definition, there exists V in S, such that L of V equals W. Next, consider alpha times W, which is equal to alpha L of V. Because L is linear, due to the homogeneity property, alpha times L of V equals L of alpha V. Know that alpha V is in S because S is a subspace. S is closed under scalar multiplication. So if V is in S for any scalar alpha, alpha V is also in S. We have found alpha V in S such that L of alpha V equals alpha W. Therefore, by definition, we know alpha W is in L of S, and hence L of S is closed under scalar multiplication. Next, we prove L of S is closed under vector addition. The idea is that if W1, W2 are in L of S, we want to show W1 plus W2 is also in L of S. If W1 and W2 are in L of S, by definition, there exists V1, V2 in S, such that L of V1 equals W1 and L of V2 equals W2. Now consider W1 plus W2, which is equal to L of V1 plus L of V2. Because L is linear, Due to the additivity property, L of V1 plus L of V2 equals L of V1 plus V2. Note that V1 plus V2 is in S because S is a subspace. Since S is a subspace, if V1, V2 are in S, then the vector addition V1 plus V2 is also in S. We have found V1 plus V2 in S such that L of V1 plus V2 equals W1 plus W2. Then by definition, W1 plus W2 is in L of S. Hence, L of S is closed under vector addition. We introduce the concept of one-to-one for linear transformation in exercise 21 in page 194 of the textbook. A linear transformation L from V to W is said to be one-to-one if L of V1 equals L of V2. Then V1 equals V2. That is, no two distinct vectors V1 and V2 in V get mapped into the same vector W. In the bottom of the slide, there are two figures. Both represent a function. Figure A is a one-to-one function, while figure B is not a one-to-one function, because in figure B there are two distinct vectors get mapped into the same vector W. So figure B is not an one-to-one function. In the next slide, we will show L is one-to-one if and only if kernel of L equals the set of 0V. That is, kernel of L is the set of a single element, and the single element is the zero vector in V. The proof has two parts, the if part and the only if part. To prove the only if part, we suppose L is one-to-one, and our goal is to show kernel of L equals the set of 0V. Suppose L is one-to-one. Consider V in kernel of L. Our goal is to show V must be equal to 0V. If V is in kernel of L, then by definition of kernel of L, LV equals 0W. Since L is a linear transformation, we also have L of 0V equals 0W. Since L is one-to-one, by the definition of one-to-one, we know if L V1 equals L of V2, then V1 equals V2. Hence, V must be equal to 0V, and the proof of this part is finished. Next, we prove the if part. The if part assumes kernel of L equals the set of 0V, and we want to show L is one-to-one. The idea is that given L of V1 equals L of V2, we want to show V1 equals V2. Consider any v1, and v2 in V such that L of v1 equals L of v2. Then we know L of v1 minus L of v2 equals the zero vector in W. Because L is linear, due to the additivity property, we know L of v1 minus L of v2 equals L of v1 minus v2. Now we have L of v1 minus v2 equals 0W. By definition of the kernel of L, we know v1 minus v2 is in the kernel of L. Since the kernel of L equals the set of 0v, thus v1 minus v2 equals 0v, and therefore v1 must be equal to v2. So L is a one-to-one function. We introduce the concept of onto for linear transformation in exercise 22 in page 194 of the textbook. A linear transformation L from V to W is said to map V onto W if L of V equals W. L of V is the image of V under L, and is also the range of L. If the range of L equals W, then we say L is an onto function. In the bottom of this slide, there are two figures. Figure A is not an onto function because there is one element in W that is not in the range of L. An element W is not in the range of L means we cannot find a vector V such that L of V equals W. Figure B is an onto function because every element in W is in the range of L. So the range of L equals W, and B is an onto function. In this slide, we discuss example 12. Let L be a linear transformation from R3 to R2, and L of x is defined as a vector in R2, where the first entry is x1 plus x2, and the second entry is x2 plus x3, and the input x is a vector in R3. Let S be the span of E1, E3. Here, E1, E3 are vectors in the standard basis of R3. Know that S is a subspace. Our goal is to compute the kernel of L and the image of S under L. First, we compute the kernel of L. If x is in the kernel of L, then L of x equals the zero vector. Hence, x1 plus x2 equals 0, and x2 plus x3 also equals 0. Solving the two equations, we obtain the kernel of L is the set of scalar A times 1, negative 1, 1 transpose, where A is any real number. Know that the dimension of kernel of L is 1, because there is only one freedom. There is only one degree of freedom because there are three variables, x1, x2, and x3, and we have only two equations. So the number of degree of freedom is 1, and the dimension of kernel of L is 1. Note that L is not an one-to-one function because the dimension of kernel L is 1, and because kernel of L does not equal the set of 0v, so L is not an one-to-one function. Next, we compute L of S, the image of S under L. If X is in S, then X must be of the form 1A0B transpose, because S is the span of E1, E3. E1, E3 are the vectors in the standard basis of R3. Next, we compute L of X. X1 plus X2 is A plus 0, which equals A. X2 plus X3 equals 0 plus B, which equals B. So L of X equals AB transpose, where AB can be any real number. Therefore, L of S equals R2, which implies the range of L must be R2. That is, L of R3 equals R2. To see this, note that S is a subset in R3, and therefore L of S is also a subset of L of R3. And we also know L of R3 is a subset of R2, because L of R3 is the range of L, and by definition of the range of L, L of R3 is a subset of R2. We have shown L of S equals R2. Then from the last three conditions, we can conclude that L of R3 equals R2. Note that L is an onto function because the range of L equals R2. In the bottom of this slide, there is a question. Is it a coincidence that the dimension of R3 equals the dimension of the kernel of L plus the dimension of the range of L? Here, the dimension of R3 is 3, and the dimension of the kernel of L is 1, and the dimension of the range of L is 2, because L of R3 equals R2, and the dimension of R2 is 2. Is it a coincidence that this equality holds? No, this is not a coincidence. Actually, this is the well-known Rank-Nullity Theorem. Let L be a linear transformation from V to W. The Rank-Nullity Theorem states that dimension of V equals the dimension of kernel of L plus the dimension of L of V. L of V is the range of L. Note that dimension of kernel of L is the nullity, and the dimension of the range of L is the rank. So the rank-nullity theorem states that dimension of V equals the nullity plus the rank, which is consistent with the Rank-Nullity Theorem we have learned in section 3.6. You can verify this by yourself. We have finished section 4.1, and I have selected some exercises for you to practice. The answers to the selected exercises can be found in page 506 of the textbook. In this section, we have learned the definition of a linear transformation and many related examples. We also learned the kernel of L, which is related to the null space of a matrix, and we also learned the image of S under L, which is related to the range space of a matrix. And we also learned the concept of one-to-one and the concept of onto for a linear transformation. After learning section 4.1, I hope you can familiarize yourself with these concepts. Feel free to leave comments for the video or for the course. Don't hesitate to ask if you have any questions.